So, good morning. Let's get the show on the road so we get things through in a timely manner. So, as you may see, there's a bit different layout this morning on this view screen. For some reason, the system really dislikes using full screen mode with the recording stuff, so bear with me on this one. Anyway, this morning we are continuing with the software engineering methods, and today we are going to talk about requirements, which was left out last week. Also talk about how to deal with those requirements, how to make use cases out of them, so how to go from the from the customer to actually having something worth designing with UML and doing some PCE modeling, which enables us to go from the use case diagrams and business case class diagrams to something that's actually usable as architecture. So, quick recap on last week's topics. The objects are nice things, since we can use different objects, different ways of using objects, defining methods and attributes to them to basically describe any situation or system in the world. We can describe, for example, library system, we can describe games with them, we can even describe something large like an entire control system of a factory with objects. So, with these objects or object-oriented thinking, we have the UML, which more or less enables us to define different aspects of the software we are building. Structure, for example, what sort of objects we have, what sort of components we have, how this software is deployed, do we need servers, do we need workstations, and that sort of stuff. Also, behavior, how, for example, the software will function in the organization, what sort of activities will happen when a customer or user loans a book from a library, or how warehouse logistics and billing, for example, work together to get the customer billed and get the package delivered to their home. Finally, there's also some interaction diagrams, for example, sequence diagram, which tells us or enables designers or programmers to design how, for example, server and client system talk with each other, exchange information so that client system can use the server, or, for example, the World of Warcraft function, so that the two players can see each other and function together on the same server. So these sort of things are possible with the UML diagrams or any diagram approach which uses objects. It doesn't restrict us in our design. So basically, the idea with the UML and the with software process in general is to get from users use the users and customers and stakeholders to get the requirements, and from the requirements gather enough information on what we have to do to create the analytical architecture, create the UML designs, have some sort of an idea what we are doing, and based on the physical restrictions or the real world restrictions, stuff like money or schedules or platform computing power, for example, we can go from the analytical architecture to the actual architecture. Meaning that, for example, with the analytical architecture, we can design whatever we want to. For example, create a game that is basically the World of Warcraft in mobile phone. But when we go from the analytical architecture to actual architecture, we might find out that we don't have enough computing power, or the network connections aren't reliable enough, or these sort of things. So we get more restrictions and things that require us to design things in certain ways. For example, we can design, we can design touch screen interface here, but if it turns out that the touch screens aren't robust enough, for example, in polar exploration, then we really can't design it or use it when we are talking with the actual components. So we have to consider how we actually, what sort of parts we can actually use. Of course, from the actual architecture, which is related to the real-world components, then if we know the physical hardware we are using, the requirements or things that the customers need or want, and we have a design which solves most of the requirements or all of the same requirements, and we have a layout for the architecture or how the software is built, then we simply create the source code, and when it's tested enough, when we know that it's good enough, then we deploy it, sell it to our customers, or put it available online, and so on and so on. So that's basically the idea of software development process, or the what happens when we try to apply software development methods. So overall, all the models, whether they are waterfall or rational unified process or Scrum or extreme programming or anything, they have more or less the same ideas and similar models. They start from the business case. Is this something that is needed? Could we make business out of it? Or at least, is this something that people would need? Then we initially plan something, we collect the requirements, do the analysis and design, implement stuff, test things, evaluate how well our design works, and do more planning, gather more requirements, do analysis, and do implementation, test our things, and go on and so on and so on in this central cycle here until we have good enough software or high enough quality to deploy things. First, possibly in some smaller market. For example, the Nordic markets and Canada are excellent places to launch mobile software, games, applications, and stuff, because these markets are small enough that it won't affect global sales to a large degree, and it's a place where you can launch English software or test out new ideas. People have new models of phones, have high penetration level of new high technology. So Canada, Finland, Sweden are more or less used as test beds for different software solutions, which are then aimed at larger markets in Europe, North America, Asian countries, and so on and so on. So partial deployment or full deployment, whatever you design, you do that when you are done with. Think that you have a product that has high quality. Of course, sometimes you may find out that even in the deployment, okay, the software doesn't work, or there's something missing, or the customers think that they might like the software, but for some reason the sales numbers just aren't there. There's a possibility that the business model was wrong, or it was overly optimistic, or that we missed some requirement here, for example, so that it could still be honed into much more better product. So sometimes even from deployment we go back to business modeling and design. So all I'm trying to say here is that even this model, which is more or less the idealistic model of how all iterative development happens, even the deployment isn't the last step on some occasions. For example, I know one game from local game developer, or well, from Kotka, 100 kilometers from here, which launched a rather successful game for iPhone, but found out that it's too complicated design for iPhone, so they more or less redesigned the interface, did some adjustments on the difficulty levels did some adjustments on how the game is played, relaunched the game for iPads, tablet systems, and PC, and made a killing profit with their product simply because people liked the game on iPhone, but they consider it to be more something they would play on this, more sophisticated or more technological setup for games. The iPhone simply had too small screen, and there was too many options and too many things you can do there. So, it's not insulting to say that the game required too much intelligence to be played by users of iPhone. I am myself an iPhone user. But, for example, all the requirements were there, the business model was certainly there, but when the product was deployed, they just found out that people actually like the game more when they have larger screen, or they have access to mouse or other user interfaces than just the touch screen. Okay, so why are these things happening? I know the guy who designed the game is more or less a professional with more than 15 years of game design experience, more than 20 years of game reviewer experience, so he should know why these things happen. But even still, he got some parts of it wrong. And today, the requirements, gathering requirements, and the analysis of requirements are trying to find out some answers to the question that why even professional people fail to see the faults in the design, or fail to see why their excellent software, which solves all the problems in the world, fails to achieve this objective. So the requirements gathering and why the requirements gathering step sometimes fail. Well, of course, the requirements aren't just one simple thing. Basically, they are condition or functionality that we have to have. They are functional requirements, which mean that there's something that has to be done. For example, if I press button A, the software has to draw a letter A on the screen. That's a functional requirement. Or that when I put the system online, the elevator moves up and down based on on the floors the users push the buttons, or if there's a user inside the elevator cabin, then they are able to select the floor they want to go. That's functional requirements. It's something that happens with the software, something that the system does. Of course, the other area is non-functional requirements. These are something that are more general, or even sometimes even more difficult to test or seek out. For example, the security aspects in several locations are non-functional requirements. Of course, the functional requirement is something that, like that there has to be a PIN number identification in the software. That's functional requirement. Okay, so you create the software so that it asks for 4 numbers every time you log into the software or open the software. The non-functional requirement would be that the software is secure enough so that it can be placed on a publicly accessible server on the internet. So you have to design the software so that it's actually able to withstand denial of service attacks, or use a secured communication method so that people can sniff around what the server and client are talking about. On the other way around, the non-functional requirements may be something like that the system, no matter the load or amount of users using the software, has to answer or load the screen within 1 second from the request. That's something from performance side. It's non-functional requirements since you really can't create any function that ensures that your software responds within 1 second. It's more of an architectural design or performance issue, so you aren't creating source code to answer quickly. You are designing the architecture so that the system answers quickly. Finally, on non-functional requirements, there's, well, one really easy requirement related to games development, for example, is the game has to be fun. The product has to be fun, or the product has, or in more general aspect for all applications and stuff, the product has to be easy to learn, intuitive to use, and something that people enjoy using. Of course, if you are building something for tax office, you probably don't care if the software is fun to use. Filing your income taxes rarely is fun, but it has to be intuitive to use because tax code may be really complicated. So you have to have software that's more or less helping the user to fill out their report, or at least ensures that there's the minimal risk of user giving wrong information unintentionally. On the fun aspect, well, how can you even test if the product is fun? You can interview your customers, you can interview your stakeholders, that sort of things. But that's actually much more difficult to see that it's fulfilled than, well, with the functional requirements. With functional requirements, if it says that when I press the red button, the sound plays out, and it's simple to test. Push the red button and see what happens. But if the game has to be fun for your target audience, well, then you kind of have to find out people and ask them, and then hope that they aren't just pleasing you, they are, well, saying their honest opinion. Okay, so that leads us to the requirements elicitation, or more simple terms, requirements capture. It means that it's all the approaches or things that we do to gather information about the system we are designing. Usually it means something like doing interviews or surveys, talking with the customer, talking with the stakeholders, interviewing people, see what they really think about. The same thing that we did on the first exercise event. Collect different stakeholders. What stakeholders do we have in the software project? So we go talk to them. It's, well, fairly simple enough. Ask, what are the problems with the current system? What do you think is difficult? What could be more, what is unnecessarily complicated, and so on and so on and so on, and try to find out why the people find these things problematic. And, well, of course, you have to also find what things are problematic and then design something that fulfills those needs. Of course, then after you have collected the information, you have to do some analysis work. Like I said on the first lecture, there might be people who require that their user interface is mainly red, or people who say that it should be blue, or people who say that it should have no more buttons, that it absolutely has to have, or that it has to have every functionality. Every functionality has their own button and they are always available. So actually what it means is that you have to have user interface that's adaptable or customizable for people's users. And that it might seem like a simple thing really. But when we are talking about the interviews with tens of people, tens of stakeholders, all which have at least one representative, then it may not be simple enough just to understand, listen to people, but actually you have to understand how the system is used, or how it should be used, or how the current system is used. So it's not as easy as it sounds like. So how do we do it then? Well, stakeholder interviews I already mentioned. Joint sessions with stakeholders. Well, it means that I'll collect a group of people in the classroom, for example, and start to ask from them, what is the main problem you have with the existing bill management system? How about you? How about you? How about you? Do you all agree? Do you disagree with these sort of things? And of course, we need a facilitator there. It's nice thing to do, But unfortunately, people are often busy. They join us with Skype, and when you actually listen to the Skype, you hear that constant clacking of keyboard, because they are just participating on the Skype means that they are putting their headphones on, but they are actually doing something else. So you have to get them into one room, or have to get their attention, but that means that you are more or less screwed if you want to have more than 5 participants. For example, I can tell that I had to arrange a steering group meeting for one project in last fall, and I spent an hour and a half arranging 30-minute interview or meeting with people, simply because everyone had something overlapping and this and that and those. So consider if you are actually a contractor trying to get the CEOs or the business logistics managers and stuff like people like that actually to come to your facilitation session. So, well, of course, it's a nice idea, but in the business world probably won't work. If you take, if you are building some sort of application, then yes, probably. You just get a room full of users and start to ask them, what do you hate in life? Or what do you hate in filling taxes or buying new socks or whatever? And then try to design a software that helps people who have problems finding suitable socks in their stores. Of course, when you have those main requirements, you can also help yourself by using those as a list in a contract. Okay, so you say or agree with the customer that we need to have this, this, and this improved. Of course, that's the basis for a contract. You agree on certain things that you are doing, so at least those things should be requirements. If you don't fulfill those requests, then you are not getting paid. So of course, that's one place to get the requirements. If you agree that you are trying to enhance performance of something or allow users to use internet connection or, internet services to reserve seating or something like that, of course, that's place for your requirements. And also, it covers your assets when you are trying to explain your customer that, okay, you aren't paying us enough to add this and this and this feature, which is usually problematic in software development, because if you use the requirement list as your contract, it means that you agree to do something, and if you do it in time, then you are ahead of schedule, then the customer asks for something else. Okay, now it looks nice. Can we have it available in mobile platform and stuff like that? And when you say that yes, we can build a version that functions in a mobile platform, then but it costs you 500,000 euros. Then no. We asked you to do this software. We want it to function in a mobile platform, and we aren't paying you if you don't do this. Then you at least can say something like, say that your contract doesn't mention anything about mobile platform, so the customer who requires you to do this application may go have fun time with themselves with the requirement of mobile platform if they aren't willing to actually pay for the development. Other ways, or other things that function as a basis for requirements, not only stakeholder interviews or these joint sessions with stakeholders or requirement or contracts, are also prototypes. These are really the only way to capture what the user actually needs. So people are really good at explaining what sort of things they would expect or want. They have the general idea is correct. If they have problem, they know what they need. But if you are designing something completely new, for example, the iWatch, which was just launched, the wristwatch that connects to your iPhone and stuff like that. So if someone comes to ask you what are the functions from the mobile phone you would like to have in your wristwatch, why would I want any services of my mobile phone in my watch? Well, I know that there's Knight Rider, TV show from the 80s, where the guy had basically phone on the watch. That was quite a neat feature. There was this comic character who had a similar system, but why would I ever want to have something from my mobile phone in my watch? But, well, anyway, if you want to release a watch that connects to your mobile phone, for example, to show that, okay, you have phone calls, you have messages, you have a calendar meeting, or stuff like that, which are the functions of the watches currently, you might want to build a prototype. Put some functionalities in it. People might find out that it's really frustrating to talk to your wrist when you are having a phone call. But for example, if they are just checking the time and seeing that, oh, I have missed a phone call, and start to look for their phone, that might actually be a really useful feature. So if you give the prototype to some users, they might tell you that, well, some people thought that I was a lunatic when I was on a bus stop talking to my watch. But on the other hand, the light that comes up when I have missed a phone call was a really neat feature, because I could easily check that if I have new messages without actually having to get my phone from my jacket or my briefcase during the meeting, because that would seem rude. So, okay, you have a requirement there, and you use prototype. On the other hand, with most software development suites, it's quite easy to actually create something that seems to be functioning, but it's actually not doing anything worthwhile. This is called a proof of concept prototype. It means that the system emulates or simulates that it's actually functioning, but it really doesn't do anything. It's an easy way to see if the users are able to find, for example, the different functionalities or buttons or selections in the software, simply by presenting them something that seems to be doing things. And even easier, some prototypes can be simply enough series of pictures. Okay, so if you are testing out something like a ticket buying terminal machine, you know, with the larger cities, there's on the bus terminals the system that you can use to buy tickets. So you present a picture of your new terminal system and say to customer, which button would you press on this user interface to buy a ticket? Okay, they say, oh, I would press that one. Okay, it opens into this sort of view. Put the next picture on. What would you select from this interview to pay with cash? Okay, I would press that one. And why? Because it has a picture of a coin in it. And so on and so on. So you can more or less test your design for user interface and get some ideas of why people are doing something or why they would be doing something without actually building any system. And that's really useful information. Actually, I know that I'm always coming back to games because that's one thing I have been doing for a couple of years now. But actually in one company, the level design for new level in a strategy game was built with shoeboxes and toy soldiers and sandpit and other things. It's really easy to just prototype out something. You can sort of see how the landscape or geometry works there. You can design things if you need more cover somewhere, or if you have some sniper alley you want to get rid of by placing more cars or barrels or whatever into the level, without actually having to bother your artist or level designer or anyone else by actually creating the 3D model and then seeing that, oh dear, this doesn't work at all. It's, well, the sandpit and a couple of shoeboxes and toy soldiers and stuff like that did the same thing, but everyone was able to use the plastic shovel to level out things or raise things or put the boxes in different places instead of having to have the 3D designer doing adding more hills or buildings or stuff like that into this digital 3D design. So basically, one example of using prototypes, but also one example that you can actually use your imagination when you are testing out your designs or collecting requirements or doing, well, basically whatever you want to do to design your software. Also, additionally, of course, the use cases are placed for requirements. We know that the customer has to be able to buy a ticket. We also, customer who has no idea of the language has to be able to buy the ticket so that the symbols have to work. Of course, it would be difficult to know if, for example, a person from Thailand, which uses completely different alphabet, would be able to use the software. But for example, there's actually an easy way to go around it. Just get rid of all the texts. Can you use, for example, the terminal to buy tickets if you don't have access to text, or if you have changed all the text to something like Lingonese, which no one talks? So you can test out if the system is intuitive. Also with use cases, well, you know what has to be done, so you more or less design the requirements so that if the system requires card and then PIN number and then you select the amount and stuff like that, of course you would want to have those steps without unnecessary browsing of the directory structure or stuff like that. Also, well, if you are doing something for your larger company or larger customer, you might actually get a specification document when you start to do the work. Well, it might say something like that, okay, when you install the software, it should add shortcut to desktop. That's actually one of the real requirements. I know that some Microsoft products require. And not actually, they don't require that you put a shortcut into the desktop. It's actually the other way around. It is not allowed to put shortcut into the desktop. It has to go into the directory of shortcuts into the start menu on the right place there, which no one ever uses, but that's actually one of the requirements. With Windows 8, it has to create this small box into the startup screen, but, well, on the other hand, no one I know uses the Metro interface of the Windows 8, so it's also unnecessary there. So, why do we fail then? Well, there's a list of problems. Typical problems of requirements analysis, or actually typical problems of collecting the requirements. Of course, this whole list stems from the fact that we are working with people. Some people lie. Some people say random stuff because they find it hilarious. Some people just want to please the people asking them questions so that they get rid of the situation or that the person doing the interview doesn't hate them. Of course, that's just human nature. But on the other hand, these are actually the real reasons. Like I said on my rant earlier, the users do not understand what they want. They might want to solve one problem. For example, have a warning light when we are about to run out of memory and the system is about to crash, when the users actually need software that doesn't crash. The users do not commit to the written requirements means that the users first require something, then you design something, and then they actually come up with something else, and they are really angry about the fact that, okay, you can do this, even if I wanted to have this, when they didn't actually tell you about the fact that they want to have access for the USB drive or whatever on the new mobile phone, or have memory card in their phone when and when you design a phone which doesn't allow external memory cards. Okay, well, the users want new requirements after the old ones are fixed. Means that if you launch something, then the users might actually find out or see another system that does something really nice and something really nifty, and then they just want that feature to their existing software. Of course, they won't pay you anything for development of that feature, but that's actually something, somewhat of a problem. It's called featureitis, and it means that the customers or users always want new features when the existing ones work, but they are not willing to pay for it, or if you are adding feature after feature after feature, they always come up with something new. You can please your customers or users by adding new stuff. Of course, if you are in business of running places like YouTube or something like that, of course, adding new features and adding new things and adding new content is your business. But if you are designing something like a library system or bill management system for university, adding new features or having new requirements, for example, something like that the system has to function in a tablet without physical keyboard and mouse, are sometimes really, really expensive to do. And even if they aren't that expensive to do, you should test out if the new system works. Okay, so also the users do not participate in elicitation or reviews is also the problem I mentioned earlier. You can invite people to participate on these events. They won't participate because they have much more important things to do, or they participate but they don't understand that now would be the time they would have to explain themselves if they want the feature in the software. They also don't understand that the reviews are something that they can use to request changes to the software. The reviews are usually on Friday afternoon. Oh well, I know at least one software company that always has the customer reviews on Friday afternoon, simply because the customer is, okay, we like it, can we just go home? I want to go to sauna and drink a couple of beers. I don't care what you are doing, just let me get out of here. That's a strategy. But that also means that the user or customer, or people paying for the development are actually throwing away their ability to affect the requirements and affect the outcome. So it means that the final outcome probably won't satisfy them, and they will probably hate the software, or at least the outcome won't be as great as it should be. Also, the customers don't understand technology. That is actually more of also a problem between the marketing and the engineering departments. Well, I would say that it's the stereotypical problem between the marketing and the development departments. People don't understand the limitations of technology. And that's also because unless you are familiar with the different algorithms or how search engines work and how, for example, image recognition or pattern recognition works, there's really some arbitrary requirements or problems. There was a comic on the internet a couple of weeks ago with basically illustrating this problem. There's a new software in development for people going into national parks. Okay, so the first requirement is that the software should be able to identify if the taken picture or image is from the national park. Okay, so they have access to the mobile phone's GPS. It's simple enough to see the coordinates where the picture was taken and reference that to the list of national parks to see whether it was actually taken inside the national park. It's easy, it's accurate, it always works. If you take picture inside national park, the software is always able to say that, okay, you were there, or you were there, or you were there. You were in Yellowstone, you were in Lapland in Finland, for example, Urho Kekkonen National Park or someplace else. But the other requirement was that, okay, we want the picture, the system to also say that if there's an endangered bird in the picture. So if the user has to tell the user that, okay, great, you have captured the picture of a bird, or in this specific case, endangered bird. So, okay, that requirement takes, well, 10 researchers, 10 years of time, and 10 million euros of money, because recognizing a bird, or being able to certainly say that, okay, there's a bird in that picture, is really complicated task. Not to say that actually identifying what bird there is in that picture. Of course, we all in this classroom know that this is somewhat self-explanatory. We can know where the picture was taken because we can get the GPS coordinates, but we won't be able to tell what was actually in that picture automatically, because that's a really complicated task of calculation and pattern recognition. To us, it's obvious that you shouldn't require something like that. But for example, if you are an engineer and you are just requesting something, doesn't it sound a bit strange that you can actually have easily the requirement that, okay, this software can automatically pick all the pictures that were taken in the national park from the picture bank, but it's unable to pick me the pictures where are birds. It's arbitrary. Of course, this is somewhat artificial example, but it also emphasizes the point that the users don't necessarily understand the technology or the limitations or abilities of mobile phones, smartphones, tablets, PC systems, clouds, internet, or anything. They know what they are capable of doing based on movies and TV shows. And well, you all know how accurate those are. Also, the users may not actually understand the development process. That's one of the things I always say when I'm giving programming courses. So that even if you never are going to actually do programming for a living, you should at least participate on one programming course to just understand that how the development process or development of software happens. It's not just that you are telling the computer that, dear computer, please add this and this and that. It's actually really, really complicated if we go to embedded systems or something like that. So users don't understand that. Well, I personally don't know what the car mechanic does when they are, well, replacing cylinders in my car engine. So why would the car mechanic give a damn about what I'm doing when I'm creating the software he's using to read the sensor readings with their laptop and stuff like that? Well, of course, I know how the basic functionalities of combustion engine work, or probably the car mechanic knows something about software development, having read something from the magazine. But for example, the time required to test new features or test out the system or finding functioning platforms or drivers or stuff like that is something that they don't know and they don't care about. So, of course, if they don't understand the development process, it means that they might actually ask new features a couple of weeks before launch in a year-long project. Because, well, you added those other things, why aren't you adding these things? Of course, not caring about the fact that things have to be tested. Well, I've been saying that the users are stupid. I've been saying that the people who pay for software aren't necessarily the brightest people in the industry, but that's not all. All of the blame isn't on the users or customers. Also, the developers, us, are sometimes the problem. The easiest thing to miss is that the developer doesn't understand the customer. It's not the language or the culture or the local dialect that might be the problem. It's simply because the terminology of the customer is strange or unfamiliar for the developer. For example, if you are doing something for a law firm or hospital, or basically anyone doing international business, you might not understand what the people are talking about. For example, when you are providing a hospital with some software that's used to plan for surgeries or stuff like that. There's a huge amount of tools you have never seen. There's a huge amount of terminology you have never heard. There's parts in human, the different blood veins and different organs and stuff like that. They are talking about like they were everyday occurrence, that they have one in their fridge right now or stuff like that, but you have never actually heard about what that means. More simplified, we may describe how different solutions actually affect the performance of the software or performance of the server. The customer doesn't understand us, and we don't actually understand the customer when they say that we just want it to be good. Okay, what does the good mean? Well, it has to be easy to access. Our current system has identifications and stuff like that. But of course, the developers think that, okay, well, we are providing you with the top-of-the-line server rack system here, which backups everything in cloud. Unfortunately, we are just adding 50 new security checks and features and stuff like that into the system because now it's saving stuff into the public network, meaning that the developers didn't understand what the customer wanted. Also, this is an example of the developer forcing their own views into the customer's head. So, of course, doing something right means that you don't have to do things twice. But on the other hand, if your customer just wants this small system, for example, to manage a local branch of a library network, or have a, warehouse, not warehouse management system, the product sales system for a small kiosk, you might consider that, okay, creating a software that connects into the internet or uses external server to back up everything would be the right way to do things. It would be expensive. It would have large amounts of technology. What the customer just wants, more or less, an Excel sheet filled with macros to see that if they have enough, for example, candy to sell to the customers at the kiosk. Also, finally, the analysis is done by technical experts instead of domain experts or persons with people skills. Meaning that, the engineers have the ability to understand how technology works. Unfortunately, it often also means that the engineers do not have any skills to understand how people work. I'm an engineer, I can say that. It means that the design of user interface or the design of the decisions of what are necessary things in the system are decided by someone considering all the cool features of the software, not actually paying attention what the customer needs or understanding what the customer wants. On my first lecture, I used the VCR I bought as an example of system that had a remote control which had more buttons than standard keyboard on PC. So of course, engineer might like it. Well, it was quite nice to have access to all the features, but are these things actually necessary? If we are buying VCR, or we're buying VCRs, or Blu-ray players, or stuff like that, to have it installed into a living room where we can play the Disney tapes and stuff like that for the kids. So why would we need all these 500 other features or programmable time delays and stuff like that? We don't need it. We want to, not on all occasions. So instead of actually making the system more accessible, we make it more complicated so that the standard users are annoyed with all the features and all the things you could possibly do but actually aren't able to do, and it's making learning curve really complicated for the use of that particular hardware. Okay, so a couple of words about the requirements. Of course, if we have a list of them, then we also have to do some classification for them. Some of them are more important than the others. For example, architecturally significant requirements are the ones that are affecting the basic structure of the system. They are the high risk, high priority requirements, meaning that these things obviously are important things to identify and ensure that the design caters to these requirements. Besides, these architecturally significant requirements, simply something like that, okay, the software has to be able to be used on iPhone because 95% of our users use iPhone or, Android system, or if they are masochistic enough, Windows Phone. But still, that's something that's architecturally significant. The other way of classifying things, of course, the classifications are many. You can use different ways of classifying requirements, how much time it takes to add them, how much money it takes to add them. But the one example I'm giving you is this verbs plus. It basically means that we can classify our requirements into functional requirements, usability requirements, reliability, performance, supportability, and the plus is non-functional requirements, meaning design constraints, implementation requirements, interface stuff, and physical things. So basically, classification for all these different main views or aspects. The functionality, for example, says that, okay, these define how the system behaves with the inputs and outputs. If you press a button, then something happens. If you walk past the sensor, something happens. So what happens when the system is doing something? So basically, the functional requirements are those. The non-functional requirements go to, usability, reliability, performance, supportability, and plus means, the non-functional requirements, but the constraints caused by these things and the interface and other things. So going further into usability, for example, the human attributes, aesthetics, consistency of user interface. For example, we know with the Windows Office software suite that if we press the file, there's always new, load, save as, and quit. So we have to learn that only once to know that if we want to save our work, be it Word document or PowerPoint presentation or Excel worksheet or database or whatever, we can at least make a new saved file or new saved state by choosing the file. There's always some place to get help. The view changes, for example, how these windows are organized, and of course the first place on the ribbon the ribbon interface, the home, the first one after file, includes all the basic functionalities. Those are consistency things. They are designed for usability. Other things for usability, for example, are things like is the user interface accessible for colorblind people? Does the user interface allow having enhanced contrast or large fonts, for example, for vision impaired people who still can see something but don't have the necessary eyesight to be able to use the normal software. Well, reliability, on the other hand, is accuracy of the results. For example, we always know that the calculations give correct answer. On the reliability aspect, well, the first Intel Pentium chipset actually had a problem how it rounded long decimal numbers or floating point numbers. And it actually almost bankrupted the company because you couldn't anymore rely on the results the computer calculated. This was 25 years ago, but still, it's really bad mix-up from a company that's making PC computers. If you create a processor or central processing unit which doesn't give reliable answers, you are more or less screwed. Well, also something like mean time to failure, meaning that the failure happens in average once per month or once per year. The performance is about speed and efficiency and throughput and response times and recovery times. For example, if the system crashes, how many seconds or minutes does it take to be back online? And supportability is all these aspects about testing things, adapting the system, installing it to new hardware or new server system, doing localization work, or maintaining things. For example, if you have to swap hard drives or clean out old usernames or clean out the accounts which are no longer in use. So basically, how easy it is to support the use of system, so that you don't have to do clean installation every time something bad happens. Finally, the other non-functional requirements, the plus part, include constraints on implementation, constraints on design, interface, and other physical requirements. For example, for a mobile phone, the material, the shape, the size, and weight are something that more or less dictate well, I would argue that they are more or less the first things some companies decide when they are making new mobile phone. It doesn't matter how much software is loaded into the system. It doesn't matter how much is spent on the software side of things or how well the software operates. But the first things you have to have is know that, okay, it has metallic feel or this plastic metallic combination feel. What's the shape of it, how large it is, and how much it weighs. More or less on Android headsets, that's one of the only things that actually differentiate the products between each other. But that's actually a requirement, because no matter how great the phone would be, or no matter how great the new operating system inside the new phone would be, for example, in case of Jolla, which is the new mobile, the Sailfish operating system, but the new platform for mobile phones, no matter how great the new operating system would be, no one would want to buy the phone if it was the shape, size, and weight of a construction brick. Why would anyone want that? So, of course, that's one of the physical requirement which trumps over all of the actual design requirements for the interface and other things, simply because this physical requirement means that if you don't fulfill this requirement, you don't have business, because no one will want your product. Also, things like what sort of standards we have to adhere to. In software business, not that many things really, but for example in avionics, aviation, space industry, mining, nuclear power plants, places like that, there's actually large amount of different standards you have to adhere to in your design work, in your testing work, in, well, basically all aspects of the software. If you don't do that, it would fall under the implementation requirements. If you don't do that, no matter how great your product is, you will never be allowed to use it on commercial system. So, what makes a good requirement candidate then? Well, here's a short list of steps. For example, list all properties required from the system, list all stakeholder needs, system features, software requirements, also other properties. Well, how much would it cost to add this feature? How high priority it is, or what's the risk of the software failing or the project failing if we don't do this requirement. Like I said earlier, the design constraint or physical constraints of mobile phone are probably high risk, so we have to start by designing that no matter what the costs are, or we can't add weight into the system. And we have to design everything else around that problem, no matter what it costs. Okay, so now we probably have a list of requirements. We sort of know what things are important for the product, how much they would cost, and what sort of things the stakeholders expect. So we are more or less on the arrow between the requirements and the analytical architecture. So, the first action, of course, is to do business modeling and create the domain model and business model, which are more or less the highest abstract level of class diagram. It's nothing really that complicated. We just more or less create the model where we have all the different things we have to have, the relationships between all the aspects and the data we have to manage. For example, here we have users who are students, teachers, they can exchange messages. Students are in classes, teachers are doing courses, course implementations, which are part of some course structure and so on and so on. So this is the domain model. It more or less defines the things that happen, the information that's going around, and how the different things are connected. From those domain models or business models, we can also have customer and activities, like, for example, people checking in their luggage through the system. We can use the requirements and those domain models to identify the actors, who are people or things doing things, and use cases, meaning that what sort of activities we have to do. Then we create the prioritization, meaning that what are the actually important things we have to do, and create the descriptions for those. So if we want the student to be able to enroll the course or send a message to teacher, what steps would they have to do? Well, go to the website, log into the system, press new message button, then select the teacher and put the topic and that sort of thing. So create the description of how the use case is done when the system functions. Of course, here we can use the user interface prototypes, draft the prototype or include some design pictures into the use case there. When we have the actors and use cases, we also have the domain model and business model. We more or less know what would happen in the system, who would be the users of the system, what sort of information goes around. So we more or less have the use case diagram set. For example, this is a use case diagram. Well, it's actually several use case diagrams. And we have identified actors here, potential subscribers and subscribers. The potential subscribers can be, they can order new magazine, they can provide feedback. They can also edit their profile, add new information, whereas the subscriber can read the content on the website, and they can also edit their payment preferences. If we would be creating a website, for example, for electronic newspaper or something like that. Also, advertiser can add, they can give feedback. They can send new advertisements or advertising content, and they can print reports. Know, for example, that how their advertisements have been noticed, how many users have seen them, how many users have clicked them, and so on and so on. So basically, these all are related to one system, which is designing a website for newspaper. We have users or actors, we have most important use cases. So now this would be the first step from the requirements towards the actual UML design. Identify the people who actually do something and what are the activities they should be doing. Similarly, there's another example on telesales use case, but basically when we have the actors, we can also do designs or start to design for testability. So we know that we have the users, we know what the system is doing, so we can also create test plan for further use to when the developers start to actually implement the system. We have the good place to design for testing here is that we can ensure that all the requirements are met, all the use cases are actually tested out, that we don't have anything else impairing needing requirements. For example, because we design the physical architecture or deployment later, we can just edit those things into our test plan. Well, of course, when we all know the use cases, we can also start to define the system architecture by adding new features into the class diagram or finding out new hardware or doing proof of concept prototypes. And, this is the place where we start to create the sequence diagrams or activity diagrams or that sort of things. This is also a place where we can actually go from the use cases, use cases towards a thing called BCE modeling, which I actually might not have time to go through with this lecture, but BCE modeling means that when we have the use cases and when we have the domain model, and we have the information, then we try to go from the analytical class diagram. For example, listing all the teachers and the databases and that sort of stuff into more technical definition, adding interfaces and system architecture or the interface models into the same class diagram. So basically meaning that we go from the what sort of data exists into actually thinking that how this data is handled or how the technical side of the system works. Finally, because I have to deal with the people in the lobby, when we have the use cases, the use cases usually just describe how things happen. For example, when the customer tries to log into the system, the happy path here means that, okay, can you please close the door because some non-friendly people are yelling outside the classroom. Thank you. The use cases describe how the system behaves, of course. The happy path here, I have illustrated, means that we usually just describe the nice things that happen. For example, I want to withdraw money from the ATM. I put my card in, put my PIN code in, say that, okay, I want to have 20 euros, and then the system gives me money. Of course, if I don't have money, if I have someone else's credit card, or the ATM machine isn't connected to the bank, it can't give me money, and that's a problem. But usually, it means that the happy path here describes what I'm actually doing, and this is the basically the happy path or good scenario. Of course, with the use case, we also should define what happens when the system fails, or what happens when the user gives wrong password, or what happens if I don't have enough money on my bank account, and so on and so on. This is not actually, well, this is relevant for the testers, so they know how the system should behave or how systems should react. It's also relevant to know that we have actually taken into account what happens when things go wrong, but of course it's not relevant for the usability of the system, because on 99% of the cases, the idea is that the user can withdraw money and everything is okay. But, well, anyway, these problematic situations, exceptions, errors, and alternatives should be included into use cases. For example, use case description, meaning that what I'm going to write into these boxes. I have the actor here, well, be it user or whoever, and we have the activities, what they are doing with the software. We have the list of requirements, and we have sort of domain model available. So what should we then write into one use case? Okay, so start state. What are the preconditions of the function? It may mean something simple like the user have an account, the user have a credit card, and the ATM machine is connected to internet. Simple enough. How the case starts? Well, user wants to withdraw money, they put the card in, and the card is read, and then we go somewhere from there. In what order the use case is executed, meaning that step by step what happens with the system. User put in the card, the screen says, okay, thank you, I'm processing information. Then it asks for PIN code and all the different things that happen. Basically, step by step, what is shown, what buttons are pressed, and so on and so on. So these might seem that they are, well, unnecessary information. Who can't use ATM machine? I mean, come on, really. But actually, it's important information in cases if we want to test that the system functions correctly, or if we have more abstract situation where the people doing the testing work have to ensure that all the necessary steps happen. Well, how the use case ends, I get money, I get thrown out, the system puts up an alert, the system, ATM tells me that it has no connection to the bank, so it cannot verify that I actually have money. Illegal flow of events, so what if I'm giving a copied credit card? What if my credit card number is on block list? What if I'm actually trying to use crowbar to force open the casing, or these sort of things? So, or, well, in a more sensible situation, if I'm using computer and I decide to yank out the power cord, how does the system recover from situation where it encounters unexpected error? What actors participate? What kind of data and resources are used, and so on and so on. Of course, if we want to have performance information, response time, and that sort of things, they would also be nice to add into the case. For example, logging on to the website, saying that it should say within 5 seconds that if the password is correct or not, or if there's some delay on the server side, it should give you sort of there's a delay in server, please wait, light show and stuff, or stuff like that, so that the customer actually knows that something is happening. Okay, so there's just a couple of templates I'm again running out of time, so I won't have time to go through the last topic on this lecture, but if you are anxious to know more about the BCE modeling, you can check out the course website. Of course, we will be talking about this topic on later lectures, or at very least on the second period when we are doing actually practical assignment or practical demonstration with the BCE design. So, with the use case template, well, there's a couple of things here. There's no actually really, highly defined approach into what goes into use case. But for example, the rationally unified process proposes something like this. There's an example of what happens step-by-step activities, brief description, and also later on alternative flows, invalid account, for example, invalid account information, other things, special requirements, preconditions, post conditions, and if there would be some extension points or other things, then of course they would be put there also. Other use cases, if someone decides to close their registration, different examples of how use cases are described, and third example which uses sort of a form approach. So overall, also supplementary specifications. So all the different things, requirements. This is about the requirement specification. So this is a template on how to, when you have collected the requirements actually are designing the system, where different requirements go: functionality, usability, reliability, performance, supportability, different things about interfaces, what sort of components have to be purchased, these sort of things. Of course, since this is the rationally unified process, there's also stuff like licensing requirements, legal, copyright, and other notices. Of course, like I said earlier, the UML and the rationally unified process are not meant to be used in small projects. They exist so that they can support whatever software process you might have. So if you are designing something for the object-oriented programming course, or just doing some small mobile application, you might not be interested on the legal aspects. For example, how the digital sales law in South Africa are, because you might not really care about that sort of stuff when you are just doing some local mobile application. Okay, so this is something that we have been talking about earlier. So the requirements analysis is the first step away from the customers towards implementing something. With the requirements, we create the use cases, we identify the actors, we create the domain and business model so that we know the information and different activities. These do not describe the internal data structure, or actually the domain and business models don't actually define anything about the actual interfaces or databases, or how things are connected, and for example what manages the network and stuff like that. They just exist to give an idea of who are the actors, what sort of information we have, and things like that. When we do the BCE modeling, then we go from the domain model and business model towards something that's implementable, and that's the next step of going from requirements to actually functioning software. But anyway, this morning we have been talking about the requirements and why the requirements gathering fails. We have been talking about the creation of use cases. I have been yelling about the creating of the use cases because of the interference from the hall. But anyway, the point of this lecture is to give an idea on how to collect these requirements and how to make the first step from, let's go all the way back to the top now, from the users and customers to getting the requirements lists and getting the first UML designs so that we have use case diagrams, we know how the system behaves, we know what sort of activities should happen, and then create the actual architecture. If we consider this list of different designs, we more or less, based on these activities, have the class diagram on highly abstract level with the domain model and business model. We have some sort of an idea of deployment diagram because we know that what sort of things are happening, how users should be using the software, so we more or less know what sort of parts the system will have. We have an idea of package diagram, what sort of things like servers or mobile applications or database things we have to create. We certainly have the use case diagram. That's more or less the idea of the entire process to create use case diagram and use cases. We have also the activity diagram because we can take all the use cases and summarize them into the diagram showing, for example, that when the customer walks in to the bus terminal and what happens when they buy the ticket and the bus driver gets information that, okay, someone has bought a ticket on this bus, so we should wait for that and that amount of time, or someone from the sales management sees that, okay, there's a passenger on this bus lane, we can't cancel that ride. And well, that's more or less that. On next time, when we talk about the BCE modeling, it means that we start to design something for the components, possibly even something for the state machines, something on the side of objects, and also talking about the communications and sequence diagrams. So going from these highly speculative or highly abstract things towards something that's more technical, or something that the programmers can get their hands on and start to do the development work, so that we go from just designing stuff to actually implementing stuff. Okay, I guess that's that, and I'll see you on Monday exercises, or if you don't want to participate that on Tuesday, and if you don't want to participate that, then whenever you decide that you want to participate on something.
Can I ask something about